Hello everyone. In this session, we will be discussing about acceleration analysis of 4-bar mechanism. As in the previous few lectures, we have studied about velocity analysis of 4-bar mechanism, velocity analysis of slider crank mechanism. So very quickly, we'll be starting with velocity analysis of 4-bar mechanism, and then we'll switch to acceleration analysis of this 4-bar mechanism. Consider the 4-bar mechanism ABCD, in which AD is the fixed link. Link AB is rotating with constant angular velocity, that is omega radian per second, and we know that velocity of any point on the link is perpendicular to the link, and its magnitude is omega times the distance of the point from the fixed center. So let's start with the velocity diagram of 4-bar mechanism. In this ABCD is a 4-bar mechanism. So velocity of point B with respect to A will be perpendicular to AB, yes, and its magnitude will be omega into distance AB. So first, before drawing the velocity diagram, let's consider A and D as a fixed point. So mark a point and name it as small AD. As I already mentioned, that all the namings or the nomenclatures in case of velocity had been done in this small case. So A and D are the fixed points, so we have marked it at a point, that is AD. Now velocity of B with respect to A is perpendicular to AB, and its magnitude is omega of AB multiplied by the distance AB. So from point A in direction perpendicular to the link AB, draw a vector AB, small ab, which represents absolute velocity of B, or the velocity of B with respect to point A, which is fixed. Now coming to link BC, velocity of point C with respect to B is perpendicular to BC. Yes, we know the orientation that it is perpendicular to BC. It can be in the upward or downward direction. So from point B, we'll draw a vector which is perpendicular to link BC. This small bc represents the vector which is perpendicular to link BC. Now the velocity of point C with respect to D, when we are considering the link CD, is perpendicular to link CD, and its magnitude will be we don't know the omega this time, so otherwise its magnitude will be omega of CD multiplied by the distance CD. Though we know the configuration diagram, so from point D or A, we'll draw a vector which is perpendicular to this link CD, which will meet the vector BC at point C. Then this DC represents absolute velocity of C, or the velocity of C with respect to fixed point D, and this vector BC represents velocity of point C with respect to B. This we have already discussed in details. So coming to the introduction to acceleration analysis of mechanism, let's consider a link AB in which point A is fixed and link B rotates with constant angular velocity, say omega, and it is inclined at certain angle. So the total acceleration of any point on the link is the vector sum of the radial acceleration and the tangential acceleration. That is, total acceleration at a point is equal to the vector sum of its radial acceleration and tangential acceleration. So that means total acceleration of point B with respect to A will be the vector sum of the radial acceleration of point B with respect to A plus the tangential acceleration of point B with respect to A. What is radial acceleration? It acts parallel to the link and towards center. That means the radial acceleration of point B with respect to A will be along the link AB, and it will be towards A, and its magnitude is omega square BA into BA. This represents FRBA represents radial acceleration of point B with respect to A, which is omega square of BA into distance BA, which can also be written as V square BA upon BA square multiplied by this BA, which comes out to be the magnitude of radial acceleration of B with respect to A as V square BA divided by the distance BA, and it is parallel to the link. So in this figure, which is the acceleration diagram, A dash x represents radial acceleration of B with respect to A, and it is parallel to link AB, and tangential acceleration is perpendicular to the link or perpendicular to vector A dash x. Its magnitude is equal to alpha into the distance BA, that is distance of point B from A multiplied by alpha. What is alpha? Alpha is the angular acceleration of the link. What is angular acceleration? It is the rate of change of angular velocity with respect to time, and in most of the cases when this link is moving with uniform angular velocity, so in that case angular acceleration becomes 0, and in that case total acceleration of a point with respect to another is equals to the radial acceleration. In this figure, this x b dash represents tangential acceleration of B with respect to A, and the vector A dash B dash represents the total acceleration of point B with respect to A. Clear? That means the total acceleration of a point on a link is equals to the radial acceleration plus tangential acceleration, and that is the vector addition. So now let's start with the 4-bar mechanism. So in this figure, AB is moving with uniform angular velocity, that is omega radian per second. So in this case, acceleration of B with respect to A will only be the radial component of acceleration of point B with respect to A. That means alpha, which is rate of change of angular velocity with respect to time, is 0 as omega is constant, and we are clear with the velocity diagram. So now let's start with acceleration diagram, and all the namings in case of acceleration diagram are done like A dash, B dash, C dash, D dash, etc. Clear? So now for drawing the acceleration diagram, let's consider A and D as a fixed point. So A dash, D dash are been considered at a point which is the reference point or the fixed point. So the acceleration of B with respect to A will be the radial acceleration of B with respect to A. So total acceleration of B with respect to A, that is vector A dash B dash, is parallel to link BA, and its magnitude is V square BA upon the distance BA or AB, and this V square BA we already know from the velocity diagram. So this vector A dash B dash, which is parallel to BA, is drawn, and it represents total acceleration of point B with respect to A, and it is towards the center A of the configuration diagram. Now coming to point C on link BC, total acceleration of C with respect to B will contain the radial component as well as the tangential component. So first of all, from point B dash, draw the radial component of acceleration of C with respect to B, which is parallel to CB and towards B. So from B dash, we'll draw a vector B dash x whose magnitude is equals to V square CB upon CB. That is, radial acceleration of C with respect to B is equals to velocity of C with respect to B square divided by CB, that is the distance of C from point B, and this VCB is from the velocity diagram, that is by measurement of vector BC. So B dash x represents radial acceleration of C with respect to B. Now tangential acceleration of C with respect to V will be perpendicular to B dash x or the link BC. So from point X, draw a vector which is perpendicular to B dash x, and it represents tangential acceleration of C with respect to B. And at this point of time, we don't know what is the point of C dash. So now coming to link CD, acceleration of C, that is total acceleration of point C with respect to D, will be the vector sum of radial component and tangential component. So the radial component of acceleration of point C with respect to D will be along D, and it will be parallel to CD. So from D dash, we'll draw a vector which is parallel to this link CD, and its magnitude will be V square CD upon CD. So vector A dash y represents radial component of acceleration of C with respect to D, and this again, this velocity VCD is from the vector DC, which is obtained from the velocity diagram. Now from point Y, we'll draw a vector which is perpendicular to D dash y, and it will represent the tangential acceleration of C with respect to B. So we'll draw a vector YC dash, which is the tangential acceleration of C with respect to D. The vector YC dash and XC dash, that is the tangential acceleration of C with respect to D and tangential acceleration of C with respect to B, will meet at a point C dash. Then this YC dash is the tangential acceleration of C with respect to D, and this XC dash is the tangential acceleration of C with respect to B. Now join B dash to C dash, which represents total acceleration of point C with respect to B, and join D dash C dash, which represents total acceleration of point C with respect to D, and this is your required acceleration diagram. Now to calculate or to identify the angular acceleration of point of link BC or the angular acceleration of link CD, we can calculate it from the vector YC dash and XC dash, as the tangential acceleration is equals to the angular acceleration multiplied by the distance CD. Let's do it once again very fast with the steps of construction. So procedure for drawing acceleration diagram, very fast. We have already drawn velocity diagram. So first of all, let's start with procedure and the diagram. Again, take any point A dash D dash as fixed point and draw vector A dash B dash equals to radial component of B with respect to A. Its magnitude is omega square into BA or V square BA upon AB, which is parallel to link BA. A dash and D dash are fixed point, and tangential component of B with respect to A is 0, as the angular velocity of B link AB is considered as constant. Now second step, from B dash draw vector B dash x equals to f radial CB. Again, from B dash draw vector B dash x, which is equals to f radial CB, which is equals to v square CB upon CB, and it is parallel to link CB. The magnitude of VCB is taken from velocity diagram, that is vector BC. Then from X draw vector x c dash, which is equals to tangential acceleration of C with respect to B, and it is perpendicular to B dash x. Its magnitude is unknown and it contains point C dash. Then from D dash we'll draw a radial component of C with respect to D, which is parallel to link CD, and it represents radial acceleration of point C with respect to D, that is v square CD upon CD. From point Y draw vector Y C dash, which is perpendicular to D dash Y, and it represents tangential component of acceleration of C with respect to D. Join D dash C dash and D dash C dash, that is B dash C dash and D dash C dash. Vector X C dash and Y C dash meets at point C dash. Join D dash C dash and B dash C dash. Vector D dash C dash, that is D dash C dash, represents acceleration of C with respect to D, and B dash C dash represents acceleration of C with respect to B. And this Y C dash is equals to tangential component of acceleration of point C with respect to D, which is alpha CD into CD. So therefore alpha can be calculated from Y C dash. In the same way, X C dash represents tangential acceleration of C with respect to B. So angular acceleration of link CB can be calculated from the vector X C dash. Hope you are clear. Thank you so much, and for more videos you can subscribe to my YouTube channel Gagan Bansal, or you can mail me at for any query to Gagan Bansal 12345, that is GAGAN BANSAL 12345 @gmail.com, or gaganbansal @geu.ac.in. Thank you so much.